We are now jumping over to continuous variables. Let's take a quick look at the map. For a really long time, we have been over here in this branch of discrete variables. That's not, there we go. All that's discrete variables. Spent a really long time on all that stuff. Well, now we're finally coming over here to continuous variables. And in particular, this video, we're talking about normal distributions. And it seems to me that the first thing we should probably do is talk about what continuous means. Now, we did talk about that a long time ago. Let's review. If you recall, continuous variables are variables that have in between values such as temperature, height, weight, volume. You can, it could be 20 degrees out, 21 degrees out, 20.5, 20.25. Those are the in-between values. So things like coins and pulling cards out of decks, those are discrete variables because you can't have 2.5 heads showing out of 4 coins. Now, the really cool thing is that this normal distribution is actually, even though it's a continuous variable, related to the binomial distribution. So we're going to start off by looking at the binomial distribution for 10 coins being flipped. Here's the binomial distribution. 10 coins, so n is 10. Probability of success, because it's a fair coin, is 50-50, so 0.5. Now, over here we're going to have the normal distribution example, in which we're going to be talking about a particular type of lizard whose population is determined, has a mean length of 5 inches. Now we're talking about length. That's a continuous variable. It has in between values. Lots of lizards are probably 5.1 or 5.2, 4.7. And there's, as I just said, variation. So there's a standard deviation of 1.58 in this population, and that's inches. Well, if we look at this 10 coin thing, let's actually figure out what the expected value and variation around that expected value would be. Well, we know what the equations for those are. And how utterly convenient. The mean is 5 and the standard deviation is 1.58, just like our lizard population. Isn't that fabulous? So these things match up a great deal, except this is a continuous variable and this is a discrete variable. But as it turns out, it's really nearly the same thing. If we take this binomial distribution and we connect the upper left corners of the blocks, see how well I can do this, something like that, we in fact get the normal distribution for this population of lizards. This normal distribution is continuous. Right? This is actually a function that we can actually get values in between these numbers. Now, as a function, it behaves differently than a histogram. Right? First of all, it has an equation, because we need to be able to plug in any x, and it gives us, the corresponding y. There's an equation associated with the normal distribution. Now, the equation is kind of crazy big, very complicated. Don't worry about it, actually, because it's been simplified for us. We're not really going to use the equation much. We're going to use some calculator functions and some tables in the textbook. That makes it much easier for us. And there it is in all of its glory. I got to say, the person who developed this, genius. But we have, e, the number e, we have pi, we have the population mean, standard deviation. Man, it's just all in there, isn't it? Once we have this, though, we can get any probability for any value we want. And so we can check and plug in 5. And guess what we get? 0.25. We could plug in 6. Guess what we get? 0.21. We could plug in 4. We get 0.21. Right? It matches almost exactly with the binomial distribution. Which means one important thing that we have to remember. Remember we talked about the law of probability distributions. What's the area of all of these rectangles going to equal? It's going to equal 1, which is 100%, because this should be the entire sample space, so it always equals 100%. Well, this is also a probability curve, so the area under here always equals 100% also, or it equals 1, because it's in fraction. Now, which means if instead of 10 coins, we did 20 coins, here's the distribution for 20 coins. We have, of course, more possible outcomes. So the 100%, which is the area of this distribution, has to be spread out over farther, which means, of course, it can't be as tall. Right? There's sort of a conservation of area that has to happen. So the biggest probability is 0.18, because it has to be distributed over here. And of course, we get 10 as our expected value, and we get 2.24 as our variation around that expected value. And over here, what happens if there's a different population? Maybe of iguanas. They're a lot bigger. Population average is 10, and the variation is 2.24. Amazing. The coincidence is simply astounding. So guess what the normal distribution is going to look like? Just like this binomial distribution. And there are the iguanas. And if we were to plug in 10 into this big equation with 10 in for mu and 2.24 in for standard deviation, plug it through, guess what? This would turn out to be 0.18. And if we plugged in 11, yep, it would give us 0.16. And this area under the curve is still equal to 1. So the same properties. There is one important difference. Well, there are a couple differences really, but with 20 coins, can you have an outcome of 21 or 22? The answer is no. This has a finite domain. This, however, goes on infinitely. We have an infinite domain. It's continuous. Could there be a lizard which is 21 inches long? I suppose. It'd be very unusual given this distribution. Could we have a lizard that's -1 inch long? Well, no. Physically, not really. The equation, though, does actually continue all the way, although it doesn't have much physical meaning. The question comes out is, it looks like it's getting closer. Does it ever actually go to 0? Does it actually meet the x-axis? The short answer is no, it doesn't. It's asymptotic. It will go out infinitely, technically never reaching 0. So is there a probability of a 100-foot lizard, iguana? I guess technically yes, but the probability is so astronomically small, it's somewhat ridiculous. So now let's look at an actual example. The average teenager sleeps, on average, it's a little redundant, sorry, 7.49 hours each night with a variation of 1.78 hours. So let's get to the question part. What's the probability that a randomly selected teenager will sleep between 4 and 7 hours? Now this is a range question. It sounds very much like some of the binomial probability questions, and it is. I'm going to show you a couple ways of doing this. Let's first of all draw the probability distribution. And you're going to be drawing normal distributions a lot, so just kind of get used to drawing out a generic normal distribution. We know that the mean is 7.49. We know the standard deviation is 1.78. We need to figure out, well, where in this distribution are the numbers 4 and 7? To do that, I like to use the standard deviation. You can see there's a curvature that's kind of facing downward here. And that curvature changes. No, here it's kind of facing upward. Well, there's a point of inflection, if I had drawn it well, on both sides, symmetric. The normal distribution, just like the binomial, is symmetric. And this distance to that point of inflection is 1 standard deviation on each side. So that gives us a nice point of reference. We can go 1.78 plus, or 7.4, that's supposed to be a 9, plus 1.78 and minus 1.78, and we get 9.27 and 5.71. Well, our 4 is still sort of over here. What we can do is go another standard deviation out. So this distance, again, be probably around here. All right, we get another point, which is 2 standard deviations out, which gives us 3.93 down here and 11.05 up here. And we could go 3 standard deviations out. The reason I might want to do that is because what is 3 standard deviations out, right? That's the boundary of outliers. Starting to refer back to some of the descriptive stats that we've done. So if a student were to sleep 13 hours, or a teenager was to sleep 13 hours, that would be an outlier. That would be pretty unusual. I'm not entirely sure how unusual it really is, but I kind of made these numbers up. And if they slept only 2 hours, that would also be unusual. Hopefully you don't do too many all-nighters. So now we can actually locate where our 2 points are. We have 4 and 7. Well, this is 7.5. So 7, and this is 5 3/4 almost. So I'd probably say it's somewhere around here. There's maybe our 7. We don't have to be terribly precise. We do need to be reasonably accurate. Right? It's in the right ballpark, but it doesn't have to be terribly precise. And 4 looks like it's just a little bit above this one. Right, so we have 4 is right there. Now, if we want the probability of being between 4 and 7, we're talking about an area. Now, 7 has its y value, which is the probability of getting that exact number of hours of sleep. But a range, we're actually talking about finding this area, because the area is the probability. The total area is 100%. This area is the probability of getting between 4 and 7. I'm going to show you 2 ways of finding this area. There's the best way and then that other way. The best way, I think, is using our calculators. Remember when we were doing binomial, geometric Poisson, there were those wonderful binomial PDF and CDF in this distribution menu? Well, right here up at the top, look at that. We have normal PDF, normal CDF. Which one is this? I mean, this is a collective area. So this is a CDF kind of question. So I can show you the syntax for this thing, which is upper boundary, lower boundary, mean, and standard deviation. So in this example, oops, my mistake. I switched these. It's not upper and then lower, it's lower then upper. Kind of like that. So now we can plug in the numbers, which looks something like that. So on the calculator, we get a normal, oops, not PDF, normal CDF 4, comma 7, comma 7.49, comma 1.78, and we get 36.7% chance. Pretty easy and quite precise. Now, I mentioned that there were going to be two methods of doing this. This is the best method and then the other method. The other method is more traditional. In just about every stats textbook on the planet, you flip over the front cover and there are tables for the normal distribution, which looks something like this. And here we have it says area of standard normal distribution. This whole standard business means it's been centered around 0, a mean of 0. Which essentially isn't terribly important. What's important is that it gives us this area. You know, it means it can apply to really any distribution. And look at this, Z, that should look familiar. We did Z-score earlier. All this stuff is based on Z-scores. Right? And if you remember, Z is the number of standard deviations away a particular number is from the mean. Let's actually get the Z-score for this question. So we have, of course, two boundaries, so we have two Z-scores. The Z-score for boundary of 4, Z-score for boundary of 7. The distance that the 4 is from the mean divided by the standard deviation. So 4 is 1.961 standard deviations away from the mean. And 7, of course, is much closer to the mean, so it's only 0.7275 away from the mean. So what we can do is go back to our table and get some areas. Now, the way the table is designed, it gives you the area to the left of one z-value. And here, this one, they break it up into really kind of two tables. This side is when z's are to the left, which would be, I guess, technically negative z's. I always think of z's in absolute value terms. And over here, we have z's to the right, which are all positive. It doesn't really make too much difference. I'd usually just use this. So what we're going to be doing is, you can think of it this way. Here's our 7, right? So we're going to get this area when we do our z of 7, which is going to be too much. We don't want all that area. From over here at 4, we're going to subtract this area from this area, and that will get us our answer, hopefully. So with this one, our z was 0.275, if I remember correctly. I'll just check that real quick. Yes, my memory did serve me well, and while I was at it, I got the z-score for the 4. All right, so how do we use the table? All right, we look at this z-score and say, all right, 0.275 right here, z. It kind of works in both directions. Notice that this gives you whole number and tenths. This gives you hundredths. So you start by going down looking for our 0.2, really, because that's tenths. It's 0.2. And all the way down here, right, here's 0.2. So we're going to start over here. Now the hundredths place, well, I guess we're going to go 0.28 because it doesn't go to thousandths. So then we just bring these together. And there's our area. So this answers a different question. What's the probability of getting, at most 7 hours of sleep? Well, almost 39% chance. We'll do the same thing for 1.96, right? So here we have 1.9, and over here is 0.6. So we're going to come in. There's our area, which is quite a bit smaller, as we would expect. We're down at the small tail end of the curve. Once we have those, well, it becomes fairly straightforward, just subtracting. And we get a probability of 4 to 7 being 0.3647. So that's a little different than what normal CDF gave us. Which one? I mean, they're pretty close. And they're off in the 10th place. Or, sorry, 100th place. All right, now notice when we use the table, we had to round these numbers to the 100th place. We used 0.28 and really 1.96. So I guess it kind of makes sense that the round-off error happens in the 100th place. I think the normal CDF is probably a little bit more precise because there's no rounding, or at least the rounding hasn't happened at the 100th place. So that's how you find regions, answer questions which are a range of values. Let's now talk about question B, which will not be a range. So now the question is, what's the probability that a randomly selected teenager will sleep 9.5 hours? Right, not a range anymore, a single value. Right, we can still locate this on our curve. 9.5 would be a little bit past here, be somewhere in this vicinity at 8.5. This is single value. All we're looking for is the y coordinate. That's our probability for that one value. Two ways of doing it. The best way and the really not so good way. Best way, of course, calculator. Instead of normal CDF, we'll do normal PDF, right? Probability density function, right? Instead of the collective density function. So, number one, the syntax I can write out for you. We need the value that we're interested in this case 9.5, the mean and standard deviation. So we can plug in 9.5, 7.49, and 1.78. And we get 11.8% chance. So this is how you should show it. While you're writing down your work, make sure you tell me what the function used and the inputs and the outputs, and you get your probability. Now the other way of doing that would be to go back, oops, not forward, but back, and plug in 9.5 in for x, 7.49 in from u, 1.78 up there, 1.78 there. Plug it all through, you should get the same value. What a pain in the neck that would be, and very prone to just calculator input error. If you don't put your parentheses in the right place, the whole thing goes south on you. So I would really avoid using that equation and use normal PDF. Now, something that for some reason confuses folks, if you think about the tables that we were using before, you can't use this to answer that question. Right? These tables give you areas, but that last question was about a single value. The table doesn't do that for you. The equation does that for you, not the table. Now we can look at something a little different about the normal distribution. The 68, 95, 99.7 rule, which Well, again, relate back to some of the things we talked about when we were dealing with standard deviation in descriptive stats. Which would be something like this: lower bound, upper bound, mean, standard deviation. The probability of plus or minus 1 standard deviation, 68%. Now remember, way back in the day when we were first doing standard deviation, I mentioned that it captures about 68% of the data. Well, this is where that number comes from. That's really comes from the normal probability distribution, which means that if data is not normally distributed, it won't necessarily be exactly 68%. The more normal, quote unquote, the data is, the closer it will be to 68%. The next question then would be 2 standard deviations. 2 standard deviations going from 161.6 to 172.4. We're now looking for all of this area. And we get a probability of 95%. within 2 standard deviations. And of course, let's go 3 standard deviations. And we get, with 3 standard deviations, 99.7% probability, which is, of course, the 68, 95, 99.7 rule, 1, 2, and 3 standard deviations away. So again, if we talk about outliers, just how unusual are outliers? We can answer that question now. Something that is outside of 3 standard deviations, either above or below, only has 0.3% chance of happening. So that's very low probability chance of happening, so it's a pretty unusual value. Now, in general, the normal distribution applies to a lot of stuff. It turns out that a lot of natural kind of phenomena like height or weight, growth kind of stuff, seems to be very closely related to the normal distribution. So a lot of time is spent using the normal distribution, but it isn't the only one. As you can see on your probability map, there we go. Normal distribution is just the first. We have t distribution, chi-squared, f distributions. There are a lot of other distributions that are used for other purposes, but the normal distribution is used very widely. There's unfortunately the use of the word normal is a common word in the English language. When we talk about something is normal in statistics, it's actually very specific. It has nothing to do whether you think it's typical or unusual or bizarre or any of those terms. Normal means it follows this equation. It's very specific and very technical, which is unfortunate that the word normal is used in a lot of different ways. So we just have to be careful about that.